Hi, everyone. My name is Ife here, and I wish to talk about a project that my team and I had developed during my bachelor's degree back when I was at UCSD. This project focuses on using some sort of a combination between machine learning and deep learning algorithms to sort of predict the taxi fare and other important information within the city based on some historical taxi trip data that includes things like taxi details, pickup time, pickup location, pickup destination, that sort of thing, to sort of optimize the city transportation management. Um, let's see. So essentially, what we did is a combination of several simple machine learning algorithm models and one deep learning algorithm, which is MLP. What we did is that we use all of these for simple machine learning algorithms like GBM, random forest, naive Bayes, and linear regression to predict the output out of over 1 million training data to get a model out of all of these for machine learning algorithms, and eventually get a output out of the over 300 testing data set. And then we would combine all of these four output entries and combine them into another training data with four columns and feed it back into this MLP model to eventually get the final output of the original testing data set. That's essentially the strategy we adopted during the entire process. And okay, so that's what we did. And during the entire project, what we did initially was actually data processing. Because, for example, this is the graph that we draw based on the taxi trip, this sort of feature out of over 1 million training data set. And you can see that this data is highly skewed to the left because there are some significantly heavy outliers lied at the right side of the data. So we have to sort of using some techniques to eliminate all of these outliers. And also there are both numerical and categorical data within the initial training data set. So we have to use some sort of techniques like one-hot encoding to transform all of those categorical data into numerical ones. And eventually, the input dimension is 589. That is our final output. And again, this is just the initial MLP. If we were trying to use MLP, only MLP for our model, but eventually we did not adopt this methodology. Anyway, if we were trying to use only MLP, that would be it. We would design 3 hidden layers. The input dimension would be 596, and the hidden layers would reduce the dimension to 128, 64, 32, and eventually 1. We have adopted ReLU as the activation function, and the dropout rate is 0.25, and we have used MSE as our final loss function, although not strictly MSE, actually. Because MSE is so large that we actually square rooted this. It's not strictly MSE anyway. Yeah, actually, we also did some explorations when we finally determined this kind of model. We initially tried to use linear regression instead of MLP as our final, trying to determine the weight of all of these simple machine learning algorithms, but it's just turned out that this way would be a much better way because the loss function is actually smaller. The loss value is actually smaller with this model. We also did some other explorations like what we did in MLP. We first tried 6 hidden layers, 3 and 4 hidden layers. The dimensions is different. We also tried out different dropout rates like 0.5 or 0.75. We also tried some other activation functions. We also tried some other optimizations because in fact we did not use some stochastic gradient descent in the MLP. We actually used atoms. Atom and SDG are pretty much the same in our project. Yeah, eventually we did end up choosing this architecture for our MLP because it significantly the loss value is significantly fewer than the other two architectures. So why use MLP? Because state of the art is actually RNN or transformer. Even CNN is kind of out of date, honestly. But the reason why we choose MLP is simply because it's fun. Okay. A lot of people are using RNN transformer, and our team is just like, oh, it's boring. It's really boring. We would like to try something new. But meanwhile, we don't really want to simply use MLP to just achieving a smaller loss function by tuning the hyperparameters. That's also boring. Although we did do that, but it's pretty boring. So instead, we came up with this kind of idea of combining simple machine learning algorithms and deep learning algorithms to sort of reduce the training time. And eventually we did. Actually, this kind of model reduces the training time from like almost 4 minutes per epoch to roughly 2.5 minutes per epoch, a significant reduction, roughly 25%.